Okay, so before we start the notes for day 7, why don't you take a minute and pause the video and try this multiple choice question what is it asking you here? It says, what is the slope of the tangent to the curve y cubed minus xy squared plus x cubed equals 5 at point 1, comma 2? Okay, so if you're tuning back in, I'm assuming you've paused the video and have gone through the implicit differentiation and come up with the answer. And we're going to go through the solution now. So this is obviously an implicit differentiation. We don't want to try to solve for y. So we have to handle this implicitly. And us as a product rule, right? The center part is x times y squared. So we have a product rule here. We're going to have to do a u prime v plus uv prime. Okay, so let's go ahead and set this up. So differentiating y cubed is 3y squared y prime, right? It's a y term, so it gets a y prime. That's that chain rule. Because we're differentiating a y variable in terms of x. And then we're going to do the product rule, okay? So we have derivative of x is 1 times y squared plus derivative of y squared is 2y y prime and times x. And we have a minus in front of it, so we have to distribute that minus sign. So that's why I set up if I back up again, that's why I set up the minus in the brackets to get ready for the product rule to put in there. And that's just good notation. That just trains your mind, and it kind of creates a muscle memory. Trains your mind to distribute that negative sign. Okay, going on to the next term, derivative of that is just 3x squared. You're taking derivative of an x variable with respect to x. So the chain rule ends up going away because it is equal to 1. And then derivative of 5 is 0, of course. It's a constant. Okay, so assessing what we have here, let's take a second to notice that we, in the original implicit expression, we have a y term here and a y term here. So we have 2 y terms. And so we should have 2 y prime terms, and we do. So it's just kind of a quick check before I start busying myself with all the algebra. Okay, so the first thing I'm going to do is distribute that minus sign. Oh, I guess I did. Oh, this is kind of I should have looked at this closely. Let me back up here. This is kind of a cool way to get around the variables a little more quickly. Totally forgot about this. So you might have distributed the minus sign. But look at what I'm doing here. I know that I want to evaluate y prime at 1, comma 2. So I am actually putting in 1, comma 2 right away. Okay, so instead of 3y squared, I get 3 times 4 because 2 squared is 4, y prime, minus, and then 1 times 4, because that's what y squared is, and then 2 times 2, y prime times 1, and 3 times 1 squared, which is just 1, right? So what I've done is I've taken away as many variables as soon as possible. And that helps me because now I can see I just have to solve for the y prime. So now I'm going to simplify this. So that's 12. This looks like it's 4. This looks like it's 4y prime. And plus 3 equals 0. So that really helps my eye collect those y primes when I can put numbers in right away. And now I think I distribute the minus sign. There we go. And so I'm going to collect my like terms. So it looks like I have 8y prime. It looks like I have minus 1. And I'm going to take the minus 1 to the other side. Oh, and when I take the minus 1 to the other side and divide by 8, I get 1/8. So at this point, you notice I didn't finish the algebraic solution. And the reason why I didn't do that is because it's a multiple choice. At this point, I can look at that and see that y prime needs to be 1/8. So I just stop working and just circle the answer and I move on to the next problem. It's a little bit of a time saver. Okay, let's get to those notes. So these are notes for Unit 3, Day 7. They start on page 18 of your note packet. We're still working with derivatives of inverse functions, but today we're focusing on inverse trigonometric functions. Okay, and what are the most common inverse trig derivatives and how will I remember them? you know you have 6 trig functions, right? So obviously there must be 6 inverse functions, right? But we don't use them all equally. We only really focus on 1 or maybe 2. So that's the kind of the nice thing. We're going to try to we're going to look at the trig functions, but we're going to acknowledge that there's really 1 or 2 of them that they really like to use. Okay, so we're going to do the same thing with trig functions that we did with x squared in the previous day, right? We're going to look at the function and its inverse. So let's try this on a trig function. Let's start with sine x. Here it is, right? Now swap the x's and y's and solve for y, right? In order to solve for y, we have to take the inverse sine. Okay, so the inverse of sine, not surprisingly, probably, is inverse sine, right? Like the inverse of x squared was the square root of x. We had to do a little algebra to figure that out. But if you think about squaring something and what's the inverse of that, a half power probably makes sense to you because a half and a square make a power of 1. But quite literally with trig functions, we just say the inverse of sine is the inverse sine. So we just get the inverse notation there and we're good to go. But if we draw the inverse sine, that just basically means we're reflecting this over the line y equals x, right? Which means this. And that's not a function, right? The vertical line test fails. So what that means then is we have to restrict the domain so that we have a range that creates a function in order to really talk about it. So we can't really talk about this whole green thing. And this is why we have domain restrictions. Okay, and so the domain restriction we have for a sine is this, right? We say that we're going to restrict the domain from minus pi over 2 to positive pi over 2. And the reason why we do that is because if we look at the whole function, minus pi over 2 to pi over 2 sweeps from -1 to +1. And that gets us all of our range values, right? If we go beyond that, we're just repeating range values. So, so we restrict the domain to just -pi over 2 to pi over 2. And then that allows us to restrict the inverses domain to just this, which is -1 to +1, right? The y values of the original function. And so now we have this is called 1-to-1, right? We have a function and we now have its inverse because we have functions on for both of them. Whereas this was not a function because it didn't pass the vertical line test. Okay, so just a little bit about domain restrictions. So here is that, here's that inverse, right? The inverse sine of x. So its domain is -1 to 1 because that would be the range of the sine of x. And its range is -pi over 2 to positive pi over 2 because that would be the domain of sine of x. So how do we find its derivative? That's the real question. Okay, well, to actually take a step backwards and we differentiate this implicitly. So we can solve for y and we can see that, but this is not an obvious derivative, but we can differentiate this implicitly. So the derivative of x is 1. The derivative of sine y is cosine y times y prime. And so I guess I used the Leibniz notation here, dy dx, but that's y prime. So dy dx is 1 over the cosine of y. That's the inverse. Excuse me, that's the derivative. But that's in terms of y, and that's a little messy. So because this derivative is in terms of x. So we're going to use this identity, this trig identity. Cosine squared y plus sine squared y equals 1. And this is not obvious. I wouldn't expect you to come up with this on your own, but I'm just trying to give you a little background about where the derivative of the inverse sine comes from in terms of x. This is the derivative of the inverse sine in terms of y. We just need to get the variable correct. So I'm going to solve for cosine of y, right? We're going to take a sine squared of y to the other side and square root it. I'm going to put it in here. And you might think, well, gosh, that looks messier, and it does. But this gets us something. So because we know that back from here, that x is sine y. So sine squared y is just x squared. So this is just x squared. So here is our derivative in terms of x. It's 1 over the square root of 1 minus x squared. And that is just so far-fetched from differentiating a trig function. Inverse trig functions end up looking like these rational expressions. And it's because of this process of implicitly differentiating and then having to use this identity to get back to the variable x. We're not going to do this for all 6 derivatives. I just wanted to show you where the inverse sine comes from. And then now we just need the inverse cosine. We can follow a similar process and get that. But we just need to look for patterns here so we can remember these. That's the biggie. Okay, so notice that the inverse sine, we derived this, right? It's 1 over 1 minus x squared. Let's look at the inverse cosine. I mean, it's the same, it's essentially, not essentially, but it's really similar, right? 1 on the top, 1 minus x squared on the bottom. It's just negative. So I think we can kind of relate back to just regular trig functions, right? The derivative of sine is cosine, but the derivative of cosine is negative sine, right? All the co-derivatives are negative, and that's true here too. The derivative of the inverse cosine is a negative value. Derivative of the inverse sine is a positive value. And that pattern continues. Now, you can do a couple of things. This is the one rare time where I'm just going to ask you to memorize them, right? We're not going to go through and derive all 6 of them like we did with the trig functions. You can actually program these into your calculator using your program key. And if you want to learn how to do that, I can show that. I can show that to you. Just let me know. Okay, so we're really, once we see the patterns and we can kind of internalize the derivatives, we're going to work with them and incorporate things like a chain rule. That's really where this is going to be used on multiple choice questions. Okay, so here are the 6 functions. Here are my sine, tangent, and secant. So we derived this. My tangent looks like this, just 1 plus u squared in the denominator. These are all the chain rules, right? The du dx. And the inverse secant looks like this, which is crazy, but crazy complicated. The nice thing is that we rarely use the inverse secant, so don't worry yourself too much about trying to remember that. And here are all the cofunctions, right? Cosine is negative. Cotangent looks like tangent, it's just negative. Cosecant looks like secant, it's just negative. Okay, so if you can remember these 3 and remember that the cofunctions are all negatives, then you're good to go. Okay, just a quick note on expressions. College Board uses sine -1 of u, but you can also call it the arc sine. Arc sine is nice for word processing because you don't have to superscript anything. So a lot of times College Board will call it the arc sine instead of the sine in the inverse sine. Okay, so how do we use this using the chain rule? So here is a question: if y equals arc sine 3x, then find y prime of a quarter. Okay, so we know y prime is, now this is where the chain rule comes in. Actually, let me back up here so that we can look at the chain rule. So this is what we, this 1 over 1 minus, the square root of 1 minus u squared is what we derived. Du dx is the chain rule. So this is the derivative of the outside, 1 over 1 square root of 1 minus u squared. This is the derivative of the inside, du dx, getting back to that variable x. Okay. So this is what I like to do. It helps me visually. I know I need arc sine, so I set up this basic structure with nothing here, and I know that whatever is in the brackets here goes here. Okay, and then I need the derivative of whatever's here, right? I need the chain rule, and the derivative of 3x is 3. So there's the derivative of the arc sine of 3x. So I've got the outside derivative, the arc sine pattern, and then I've got the inside derivative of 3x, which is 3. Now I can go ahead and put in 1/4 here. So, I guess I simplified this to 9x squared, and I put the 3 in the top. Now I can put in the 1/4 and simplify this. So this is 1/16, right? Because I have to square it. So this is 9/16. And this is 16/16. So 16 minus 9 is 7/16. So there's the derivative. 16 is a perfect square. Let's see if I simplify this even more. Yep, I do. I call that 4, and I put the square root just around the 7. But this I can really take the reciprocal and multiply. So that brings the 4 up top, times 3 is 12, and the root 7 is in the bottom. So this is how you see the answer on a multiple choice. All right, let's try the tangent. So we know the pattern for the tangent is 1 over 1 plus whatever is in the brackets squared. So that's where my 2x squared goes, because that's what's in the brackets. Now I need to differentiate that, and the derivative of that is 4x. So that's the derivative of the inverse tangent of 2x squared. I think I just cleaned this up by simplifying the bottom and putting the 4x on top. So it looks like that. So there's the derivative of the inverse tan of 2x squared. Okay, let's do this one, inverse cosine. So it's a cofunction, so we know it's negative. And we know it looks just like the sine function. So I'm going to copy this structure again. So I've got that structure with my negative. And so I know that whatever's in the brackets goes right here. So that's 1 over x. And then the derivative of 1 over x, that's x to the minus 1, right? Using the power rule, bring down the minus 1, x to the 1 smaller power, which is minus 2. Okay. And then, so I have a minus and a minus, so this ends up being positive. X to the minus 2 really should go in the denominator. So it looks like that. And I'm not sure if I simplify it any more than that. I do. So let's take a look at how we got from here to here. So underneath this radical, this 1, I'm thinking about this 1 as x squared over x squared. So I have x squared minus 1 over x squared. And x squared is a perfect square, so that comes out as x, which cancels with one of these x's. So I have x times the square root of x squared minus 1 in the bottom. That might be a big jump. You might need a couple of steps in there. Okay, when we get into the classroom, we'll go over some inverse trig. And I think we have a quiz today in class. Don't quote me on that, but let me just check. I'm just checking the notes real quick. Yes, we have a quiz today in class. So we'll take that quiz and actually, yeah, and then we'll do our topic questions, and then we'll be good to go.